Well, welcome everybody to the Cerebral Blood Flow virtual seminar series for today. Today we have a great lineup of speakers with Justin Lawley focused on the impact of gravity on cerebral blood flow. And then we have some great abstract speakers as well. For those of you who don't know me, my name's Caroline Rickards. I'm a co-organizer of this seminar series with Pat Brassard also, who's here as well today. So just in terms of a few notes here, this is our Cerebral Blood Flow virtual seminar series that has been running since July of last year. So we have one more session scheduled for this year. And then after that, we'll be coordinating for the fall. So please stay tuned for that. In terms of a few notes here, we have some information here regarding a point-counterpoint series that's being coordinated with Jürgen Claassen, who's an associate editor of the Journal of Cerebral Blood Flow and Metabolism. If you're interested in submitting a proposal for this point-counterpoint series, please reach out to Jürgen. His email address is listed here on this slide. And this will also be part of the recording today, so you can capture that information as well at a later date. Also, if you would like to be a member of the Cerebral Autoregulation Research Network, this is a network that was established in 2010, which is a multidisciplinary community of research working on various aspects of cerebral blood flow. And there's physiologists, clinicians, and engineers are all part of this group. If you'd like to be a member of CARNET, then please send me an email with your CV. There is no membership fee at this time. And you can also visit our website listed here on the slide as well. And for those of you who've been participating in this series for the last year, you're all well aware of the rules of engagement, but just briefly to remind you to please keep your microphone off and your video off throughout the session. There will be time at the end of each presentation for questions. And we've traditionally just been taking the questions in the chat, so if you can type your question in there and we'll ask it for you. Alternatively, if you'd like to ask a question, you can actually turn your mic on as well. Just raise your hand if you'd like to ask a question and we'll call on you to do that as well. As always, this session is recorded and posted on the Cerebral Autoregulation Research Network website within the next week. And thank you all for your support of this seminar series. Okay, so moving on now to the session. As I mentioned at the beginning, we have Justin Lawley, who is a professor at the University of Innsbruck in Austria. And Justin will be focusing his presentation today on the impact of gravity on cerebral blood flow. So Justin, I'll pass it over to you.
Great. So first of all, of course, I'd like just to start by thanking very much Caroline and Brassard for inviting me to give a talk in the seminar series. I've really enjoyed the whole series, both last semester and this one. Really catching up with so much great physiology from experts around the world, and I think it's been a real just a fabulous sort of platform, especially in these times of COVID and so on. So I appreciate the invitation very much. So of course, as we all know, humans have evolved really under the constant weight of Earth's gravity, and while we have developed many different systems and to cope with changes in posture, because of the shapes of our body are very elongated relative to gravity, we are particularly susceptible to gravitational gradients. And this week, I don't really want to try to focus too much on intracranial pressure and gravity, because I know the next seminar is a focus of that work. But what I would like to do is just spend a little bit of time talking about cerebral perfusion pressure. And that's because even recently, I've read a few papers where they have said that during changes in posture, so moving from the supine to the upright position, there is a decrease in perfusion pressure to the brain of around about 20 or so millimeters of mercury. And I don't really think that's correct. And so I just wanted to sort of talk about that for a few minutes. And one of the reasons why I think potentially is that we see this sort of classic figure in a textbook. And two of the things that it generally forgets to mention is, one, here it has the mean arterial blood pressure of around about 90 in both positions. And of course, that is neglecting any sort of sympathetic activation that we have when we're in the upright position, and generally an increase in mean arterial blood pressure at heart level. And also it neglects the other side of the coin. So we have mean arterial pressure perfusing the brain, but we also have intracranial pressure. So it is the, oh, somebody had a chat solution. Someone said you don't see any slides.
I can see them, Justin.
Oh, okay.
So
yeah, we're missing the opposite side of the equation. So I just want to slowly go through, and it's a bit of a, I guess, a complicated figure, and I've really taken data from around 6 or so different studies, and I'm really just presenting a drawn schematic, but it's taken from all these different studies about what happens to both arterial pressure, intracranial pressure, and then cerebral perfusion pressure when we change posture. So in the supine position, it's quite simple that we have a gravitational vector in this direction, so in the GX, pushing onto our chest slightly. So that means along the body, along the long axis, we have basically arterial blood pressure around about 100, and also at brain level, it's about 100. Central venous pressure is about 5, and if we follow this fluid column up into the brain, to around the sagittal sinus, it's a little bit higher, 8 or, I mean, it could be 9, I guess, or so millimeters of mercury. And that's because the sinuses are also encapsulated in an intracranial space. And then we have our intracranial pressure around about 12. And of course, intracranial pressure is higher than sagittal sinus pressure, always, because we need to move CSF out to the brain through those acranoid granulations and so on. So as we go then to the head down tilt position, the physiology actually is quite simple. Basically, we now have a hydrostatic column, and it depends how steep the angle is. So if it's -20 or 30 or so on. And if, let's say, arterial blood pressure is 100, and again, I'm simplifying, having no changes in, let's say, sympathetic activation, but that means that arterial blood pressure at brain level will basically be higher in proportion to this hydrostatic column. So for example, oh, sorry, let's do venous pressure first, sorry. So we go along, again, this is an open fluid column, so it's higher. Intracranial pressure will be proportionally higher, again, because intracranial pressure must be higher than sagittal sinus pressure as part of the Dadson equation. And then, so we have let's say, a pressure around 20. But mean arterial blood pressure will also be higher, again, proportional to this length of this hydrostatic gradient. So we end up basically with a cerebral perfusion pressure that hasn't changed, although we had a change in intracranial pressure. Now going into the upright position, it's a bit more complicated. So now we have let's see, a mean arterial blood pressure, and again, I've made up some numbers around 110 or so millimeters of mercury at heart level. And that's because we're having some sympathetic activation and an increase in blood pressure. We have a decrease in central venous pressure due to gravity. And then we must, as the first sort of schematic showed, take off this hydrostatic column. So it ends up being around about, let's say, 90 millimeters of mercury, once we account for the fact that mean arterial pressure is a little bit higher. So if under normal circumstances, this was a continuous fluid column, and already CVP is around 3, we would expect intracranial pressure to be very low, around minus, let's say, 15 millimeters of mercury. But that's not the case. When we actually take measurements, it's much higher than this. And this is because, and it's a lot of work done by Anders Öklund and Jan Malm's group, if we just focus here on this picture around the veins, we actually have a collapse of the internal jugular veins. So it goes to around atmospheric pressure of 0. And we then get a new hydrostatic sort of set point. And you can now see that this distance between the collapse of the jugular vein and brain level is much smaller. And we end up with let's say, a sagittal sinus pressure around -4, and then an intracranial pressure around -2. And this is taken from, again, measured data. And of course, we end up then basically overall with large changes in posture with no changes in cerebral perfusion pressure. During the negative parts of tilt, we have almost a linear relationship between intracranial pressure and tilt. We have done some experiments once in Rob Roach's lab, just we were practicing some techniques and we tilted him all the way head down and pressure goes up very, very high. It's almost a linear relationship. And then there's this non-linear relationship towards the upright position because we need to account for this, basically the collapse of the jugular. And overall, I don't really want to go into too much details, but this is probably a very complex regulation actually between intracranial pressure, baroreflex activation, the compliances between all the circulation. So you have the hydrostatic indifference points of the venous circulation, the arterial and the cerebrospinal fluid. Most people forget that the cerebrospinal fluid is a continuous column, and we have a compliance in our spinal sac and also very minimal, but some in the brain. And actually, all those pressures and so on are generally quite well regulated, so perfusion pressure stays very, very well maintained. So if perfusion pressure is well maintained, then let's take a look at what some of the data says about cerebral blood flow when we just do a very simple posture challenge on Earth. So I'm going to show this figure quite often throughout my presentation. It's because we do several techniques to measure brain blood flow. So we have one where we're going to measure what we call total cerebral blood flow, and that's blood flow coming in the vertebral artery and also at the same time in the internal carotid artery. We have on the y-axis total cerebral blood flow in the seated and then the supine position, and there's around about 30 minutes or so between these two postures. So we always take a time between postures to account for any fluid shifts. And you can see that total brain blood flow is lower when we're in the seated position. If we look at the anterior circulation, and again, in a lot of our studies, we try to complement these measurements. So here we're measuring, again, the ICA, but we're also measuring it in the in the middle cerebral artery. So these are independent techniques. And of course, when they tell the same story, a very powerful message on the accuracy of these data. And I think it's quite compelling that with a change in posture, there's a quite profound decrease in blood flow to the brain in the seated position. And this we don't see so much in the vertebral artery. So again, perfusing the posterior part of the brain. And these data are some of our unpublished work from Dr. Levine's lab, but they're not really novel. This has also been shown previously. So I have, again, some older data from around 2016. We have blood flow total, actually, I think this is, blood flow on the y-axis of either the internal carotid artery and the vertebral. And you can see that as they move from the supine to the seated position, ICA blood flow goes down, and vertebral artery blood flow doesn't seem to change all that much. And a similar story, really, if rather than the seated position, we do a bit more of a stressful challenge, so a head-up tilt, we see blood flow again in the ICA, so the anterior part of the brain going down quite uniformly, and the vertebral artery not seeing much change at all. So when we look at some of the potential mechanisms for why this might be, here we have mean arterial blood pressure, but this is taken again at heart level, so from a blood pressure cuff. And again, I've already explained, so I won't go into great detail, but once we add on the different effects of gravity, we actually have a similar cerebral perfusion pressure. So we don't think it's anything to do with perfusion pressure per se, but we do have quite, I would say, a prominent hypocapnia. So end tidal CO2 is around 39 millimeters of mercury, so in the seated position, and around 43 when we're lying supine. And I just want to also just remind you to remember that just for a little later on in the presentation, that at least when we're transitioning from the upright to the supine position, it's the internal carotid artery that seems to go down and the vertebral artery that stays very similar, despite a decrease in end tidal CO2. So just some preliminary take-home messages for this part of the talk is that in healthy individuals, cerebral perfusion pressure, at least at brain level, is minimally affected by changes in posture. However, cerebral blood flow is reduced at least to the anterior part of the brain. And in my opinion, at least, while hypercapnia seems to play a major role in the reduction in the internal carotid artery, I think what we do forget, and there's very few data out there actually measuring changes in fluid shifts when we change posture. And of course, if we go into a different posture and we have some sort of fluid shifts that may change the hemoconcentration and increase oxygen content, then the decrease in brain blood flow is not really a problem. It's actually a proportional decrease in flow for an increase in content. So we may maintain our arterial oxygen delivery just constant, just fine. So that probably depends on the severity of the posture challenge and also the duration, how long after the change in posture you take the measurements. So with that in mind, I just want to move on to another part or another way of challenging gravitational gradients, and that's parabolic flight. For those of you who aren't up to speed with parabolic flight, I'll just give you a very quick summary in that we go on board the 0G plane. It flies level for a period of time. So this is a 1G, so normal gravity on Earth. And then it performs a parabolic arc. And during this part where the plane is flying upwards, we actually have 1.8 Gs, so almost 2 times gravity as the plane goes over. And then once it goes over the top, we have a period of 0 gravity, and it's completely 0 for around about 20 seconds or so. Then the plane will come down and then begin another parabolic arc. And the reason why I just want to give you some details about that is because this phase of the parabolic flight is quite important depending on which posture you're in. So just show you a couple of images. This is a picture from a parabolic flight that we did several years ago, and the person is lying in the supine position. So you can imagine that as the plane is flying upwards, we have 1.8 Gs pressing onto the chest, but it's a very, very small gravitational gradient. And then when you go into 0G, all gravitational gradients are removed, of course. This is different because there's been several studies recently measuring brain blood flow during parabolic flight, and of course, really nice studies done very well. But what you have here is 1.8 G in the upright posture. So now you have twice gravity pulling blood all the way from the head into the feet, and then all of a sudden, just like with a snap of a fingers, you are having this rapid increase in central blood volume. So again, not that the data is incorrect in any way, but the interpretation could be quite different. So I just want to show you some of those data and some of the things that we have collected over the last few years. So with that vein, I just want to show you some intracranial pressure recordings. For those of you who haven't seen these before, this is during parabolic flight. On the top bar here, we have intracranial pressure. This is measured directly and invasively inside the brain. That's why it's in such a high resolution recording. And on the bottom, we have basically the gravity from the accelerometer on the plane. And the most important thing to note is that, of course, as we have that 1.8 G, pressure goes up, goes up slightly. But the important point is as soon as you go into the 0G, ICP goes down and it continues to fall. Then the plane goes up to 1.8 G, goes up a small amount, then back down, up and down. And it's, I can do this 10 parabolas, 100 parabolas. It doesn't matter. Every single subject, every time has this profile where ICP is not higher. This is the supine position. And if anything, it's much lower during the 0G phases. So as part of this sort of broad part of studies, we actually had the opportunity in some of these subjects to have them do the opposite. At the end of the parabolic flight, we set them into the seated position or standing upright position. Here you can see now we went into the seated position. I think pressure in the brain goes down because pressure in the brain is much lower in the upright position. Again, the plane is flying completely level. It's a completely normal response. But the difference here is that when the plane is doing the 1.8 G maneuver, rather than pressure in the brain going up, of course, you're rapidly unloading the brain, you're unloading the heart. And then as soon as you go into the 0G phase, you're having the opposite effect where pressure in the brain is going up. And this is because you're applying that 1.8 G to a very large gravitational gradient all the way from the head, all the way to the feet. So that's just a caveat really for some of the experiments I'm going to show you now. So this is a really nice study from Timo Klein a few years back, and it's nice in that it uses transcranial Doppler. So it has a really nice high temporal resolution. And again, I've just redrawn this data, and you can read their paper. There's statistical significances all over this waveforms, but I just want to go through sort of some of the physiology. So what you can see, again, the plane is flying level. It performs the 1.8 G maneuver. Of course, we're unloading the heart, if I remember correctly. So most likely heart rate in stroke volume is going down, or stroke volume is going down. We're having then some, really a decrease in cerebral blood flow at the same time. I guess maybe there's some autoregulation here, trying to compensate. And as the plane flies over into 0G, we have this rapid fluid shift, just like I just showed you in the brain, but also in the cardiovascular system. Blood pressure goes skyrocketing up, cerebral blood flow goes up, and then it comes back down, again, following blood pressure. And perhaps we have this interesting, again, maybe compensatory part. But the point is, for me at least, that these are really interesting data about how the brain copes with gravitational stress. But of course, there's no real steady state. And we can't really say at which point here would the brain have been in had this parabolic flight lasted, 20 minutes or an hour or 2 hours or a lifetime in space, because it's trying to dynamically adapt to this, rapidly evolving change in mean arterial blood pressure. There's also another study just a few years after, it was published just recently from Damien Bailey's group, and they used the technique as well, like I showed you before, looking at both the vertebral arteries and the internal carotid arteries. And for the most part, again, I'm not going to go through all the details, but the main result of this study was that there was some interesting findings where blood flow was high or higher, but only in the hypergravity phase. And again, that is because you're having these rapid shifts. I mean, it's almost like rapidly transitioning from the supine to the upright position 20 times or 40 times in a row. So this was the interesting finding, but really, if we talk about microgravity, which is here, it's almost the same as the pre-flight level. And one of the things that they noticed was that there was a correlation between the blood flow in the vertebral artery and then a measurement of what this is a marker of the integrity of the blood-brain barrier. And the problem is with some of these data, of course, is the media get hold of this. And while I was doing some literature search for this presentation, clearly the local Welsh media has extrapolated here quite a bit, because now it seems that astronauts' brains are becoming leaky in space, and unlikely to be probably the case. This is it would be very interesting to see whether you see similar changes in S100 beta or other markers if you were to rapidly change someone's posture over and over again 40 times. But this is the fault, unfortunately, of the media taking advantage of the data. And actually, when I plotted the numbers from Damien's study, looking at total cerebral blood flow and also some unpublished data that we have in the supine position, we had a really great sonographer on board our parabolic flights. And basically, there's nothing there. The brain blood flow, for the most part, stays quite stable, despite changes in gravity on board parabolic flights. So next, I want to go away from parabolic flight and more into terms of looking at bed rest. And one of the things that I just want to point out about bed rest is, again, it's all about interpretation and about the relevant posture. So here, of course, we have a classic bed rest study, and this is the GZ gravitational gradient. And in terms of the heart, we have a positive gradient. So from the feet all the way to the heart and the chest. But of course, it was at least quite common in I don't know, maybe 5 or 6 years ago, to allow patients in bed rest to have quite a significant pillow. So you can imagine that actually there is a gravitational gradient on board the brain. And I didn't have time to actually dig out the figure, but we actually did this experiment in part of our studies, and we showed that simply putting the head on the bed of a pillow substantially lowers intracranial pressure. You don't need much of an elevation to cause a decrease in ICP. So what does that mean? I mean, I think that's up for the person and the model for which you are trying to understand. Of course, the heart is loaded, so that's interesting. And the brain is, I would say, almost in the upright position. And perhaps that's not actually the worst position in the world for spaceflight, because we have showed that pressure in the brain is somewhere in between the upright and the supine position. But the problem is that we've never been able to find, for example, these symptoms of spaceflight associated neuroocular syndrome in any bed rest study. So the fact is they're probably just too short to incorporate this model. So it's more likely that the supine position, or some probably still use the slight head down tilt, is the optimal method. But the point is that we should always think about our gravitational gradients, and although it's very common for us to think about gravity affecting the heart all the way to the feet, we should also think about the small important gradient to the head. Okay, so again, we want to go now and talk a little bit about cerebral blood flow with head down tilt, and also with more prolonged periods of bed rest. So this is some data from, again, several years ago from the DLR. We have total cerebral blood flow on the y-axis, and we have 3 different severities of tilt. So -0 degrees supine, -6, and -12 degrees head down tilt. And what you can see is that both of these conditions decrease blood flow to the brain. And these were quite a transient effect. If I remember correctly, there was only around about a 4-hour study. So we're seeing decreases in brain blood flow within about 4 hours of changing posture into the head down tilt position. This is a study from I think Ogo just published also in the last few years. But we then, in this study, it's been taken now for 30 and 60 days. And again, similar measurements. This is brain blood flow in the open bar. It goes down, again, I think quite reliably within 30 days. And although there's no statistical difference between day 57 and day 0 in this study, I would argue that if I looked at that data myself, I would say that probably it's still lower than it was in the supine position, probably just slightly underpowered, as many of the long-term bed rest studies are. Of course, we only have the capacity to test the subjects that are involved in the study. But one of the important things, at least for me, and again, something I want you to focus on and remember for the end of the talk, is that end-tidal CO2 in this case was exactly the same in all 3 conditions. So we're seeing, unlike the changes in posture from the upright to the supine position, we're seeing a decrease in brain blood flow, which is independent of end-tidal carbon dioxide. So with these data in mind, one of the things we wanted to do several years ago was take a look at this sort of phenomena, but in a bit more high resolution. So I would say longer than 3 or 4 hours, but over several days, to look to see whether it was, what was the sort of the time course of the decrease in brain blood flow. And also one of the things that was really important to me, which was what I learned in Dr. Levine's lab, is that the thing about comparing gravity, and especially on the space station, is it's really dependent on the posture in which you compare it to. And these studies are all compared to the supine position. Well, of course, as humans, we don't generally spend most of our time lying supine, especially when we're awake. We're actually asleep. So actually what is important is to try to also compare to the upright posture. Oh, sorry. So we did a very sort of classic and simple study. We measured brain blood flow in the persons when they were in the upright position, supine, and then every morning over 3 days of -6 degree head down tilt bed rest. We used the same similar ultrasound techniques, looking at total brain blood flow and then some regional changes. And what you can see here again is, first of all, total brain blood flow. This is the increase in brain blood flow when you go from the upright to the supine position. And as a global phenomena, we generally saw this trend continuously to go down every day over the 3 days of bed rest. This was really prominent in the measurement of internal carotid artery, and again, really supported nicely by simultaneous measurements of MCA velocity. But again, I would say slightly different to the supine position. We did see a decrease in blood flow to the posterior. So using this technique of measuring vertebral artery blood flow, okay, there's some small deviation here with some statistical changes, but in my mind, these are all probably lower on all occasions, and with a small amount of variation. So I would say a general decrease in blood flow to the brain over the 3 days of bed rest. Again, when looking at some mechanisms, we don't really think there's a huge involvement in mean arterial blood pressure, because here's the supine position, and mean arterial pressure is quite constant. We know from some of our other experiments that in the -6-degree head down tilt position, pressure in the brain, at least over 24 hours, is net neutral. There's a small increase, of course, when you go from the supine to -6. This is gravitational dependent, but then there's small regulatory changes, and this goes away within a few hours. So we don't think perfusion pressure is changing too much. But we did see a relative, I guess, hypoventilation and CO2 that went down in the first 24 hours and then by 72. And again, what is just interesting as I bring it up, I don't really, it's not an experimental model to sort of isolate these measurements, but it's just interesting. If I overlay the vertebral artery blood flow onto this figure here, we see that when we're having these sort of transients where we're having strange statistical changes, they almost follow the end-tidal carbon dioxide, which is again different from what happens when we go from the upright to the supine position, where we don't really see a big change in blood flow to the vertebral artery. Whereas the ICA seems to progressively come down over days, which again, in my mind is really linking or thinking plasma volume is what sort of trends like that, at least the diuretic effect of changing, of being in bed rest. So perhaps, again, this is not an experimental model, but some interesting regional variations and also mechanistic differences between anterior and posterior components of the brain, and also different between changing gravity between the upright and supine position, and then also with bed rest. In terms of some, also just quickly mention some ideas or mechanisms here, is that you do have to, at least in my mind, think that when someone is in the upright position or the head up tilt position, the vertebral artery, of course, supplying the anterior part of the brain, perhaps is quite active with posture, visual stimuli, and so on, also perhaps vestibular. So perhaps this is different than when you're lying completely supine or slightly head down on the tilt bed, which means then CO2 becomes more of a powerful regulator. I don't really know, but at least some interesting ideas for the future. There are some other potential mechanisms, of course, is we could have, because you're in the head down tilt position, there perhaps is some capillary compression or some form of hydrostatic problems that are causing some vasoconstriction in the brain. Not really my preferred hypothesis, but I think some people have mentioned this. And then the other option, in my opinion, is probably the likely candidate is a change in plasma volume. And these have two sort of additive effects. One, we're going to, of course, decrease our cardiac filling pressures, decrease stroke volume or cardiac output, which could affect brain blood flow. And again, if we have this hemoconcentration, then we need less flow just to maintain normal oxygen delivery. So what are the keys are? Of course, we've got these, this decrease in brain blood flow. So what are some perhaps potential countermeasures? So one of the things we've been interested in, again, for, I mean, it feels like 10 years now, I don't know how many years has gone by, but is the effect of using lower body negative pressure. Actually, the LBNP has several potential effects. I'm going to talk a little bit about, again, pressure in the brain, but of course we have cardiac unloading and perhaps some changes in fluid balance and fluid regulating hormones. So it could be multifactorial, and while we don't know, again, isolating the mechanisms, we think it could be a nice countermeasure. So one of the things we do know for certain, and we have some nice data on this, is that LBNP is an effective method to lower pressure in the brain. Here we have, again, intracranial pressure measured invasively, mean arterial blood pressure, and then on the bottom panel, we have lower body negative pressure. And you can see as soon as you turn the LBNP on, we're going to lower central venous pressure. This is going to get translocated straight up into the brain, and ICP comes down really nicely, and it's a very, very reproducible result. In fact, this was a really nice and fruitful collaboration by chance that me and Dr. Devine were doing these experiments in Dallas, and we also met Lonnie Peterson and Maria Müller, and their team were doing also the exact same experiments in Copenhagen. So it was a lucky sort of collaboration together. We said, okay, well, there's no point doing even more experiments. So we merged the two data sets together. And these are two different invasive techniques. So again, very reliable. And I don't show all the individual data, but you can see here, this is the supine position -20, -30, -40, a nice reduction in pressure in the brain, pretty much all over at around about -20 millimeters mercury. And this is also probably likely because you can't have the collapse of the jugular. You can't recreate that new hydrostatic point, but that's fine for us too, because at -20, it's quite a safe degree of lower body negative pressure, because here you can see we really don't change mean arterial blood pressure very much at all. And then if you put these two together, perfusion pressure is about the same or slightly increased over time. And that means that blood flow to the brain, at least at -20 millimeters of mercury. I mean, we just did it in 4 of our subjects, but this has been done, many times by many investigators. And we know that blood flow to the brain is well maintained at low levels of LBMP. So we think this is a nice, really effective, safe countermeasure for trying to at least lower pressure in the brain. But the idea was, could it have some benefits in also ameliorating some of the changes in brain blood flow? So to look at this, we did another classic sort of 3-day bed rest study, but this time we incorporated, I would say, very long durations of LBMP. So here we have the supine position in the control condition and 3 days of bed rest, brain blood flow measured before and after. In the second condition, they also were in head down tilt bed rest, but for 8 hours a day, so from 8 a.m. to 6 p.m. every single day, the LBMP was on at -20. So we were trying to recreate almost the semi-recumbent position for around 8 hours a day. This is the typical kind of setup we had at the hospital in UT Southwestern. We had this custom-made LBMP box, which meant the subjects could roll over, they could lift their legs up and be a bit more comfortable because they're, of course, in there for 8 hours a day and they could do some work. But this also was a strict head down tilt bed rest. So unfortunately, our subjects were not allowed the comfort of a pillow. And these are some of the data. And again, it's going to be the same format as last time. So let's take a look at what happens to total brain blood flow. So here we have ICA and VA together in the control condition. So it's the same as the previous trial. We saw a good, or not good, but a reproducible reduction in blood flow to the brain, around about 300 milliliters a minute. And then when the LBMP trial was on, we had a reduction of around it was still a significant decrease, around about 100 milliliters a minute. But this is a 50% reduction. And I think what the most important point to mention here is that at this point in time, the LBMP is not on anymore. Remember, they had it on the day before, so every day. But when we're taking these measurements, it's the next morning. So this is a long-lasting and protracted countermeasure, a beneficial effect of having the lower body negative pressure device on. It was also quite effective in the ICA. And again, at least for us, it was always really convincing when the ICA and the MCAV show the same story, because they are really complementary measurements. And then in the vertebral artery, we lost, I would say, slightly because of the low subject numbers, but I would also say that probably it's having a protective effect again. So whatever the mechanism is, in my opinion, at least, seems to be quite broad in both anterior and posterior parts of the brain. In terms of some of the classic sort of regulators and mechanisms, we didn't see any significance or change in arterial blood pressure. Basically, 3 days of bed rest didn't change blood pressure on either condition. And the end-tidal CO2 is perhaps a little bit more harder to understand, because it went down slightly, maybe 2 millimeters mercury in the control condition, and then 1 or so positive, but the statistical significance is not great. And I would say that you can't argue that with a change in CO2, there's some role for brain blood flow, but I doubt that a couple of millimeters of mercury has a 50% protective role, which is what we saw in brain blood flow. So while we can't discount some role, I think there's probably the LBMP is having some other effects that are accounting for this protective phenomena. So overall, so the take-home message for this part of the whole presentation is that what I learned in Dallas as well is that if you're going to look at different physiological systems in space, we really must be careful and must know exactly which is the, and I put in air quotes, the correct reference posture, or should it be a calculated 24-hour average over the day? Because again, taking into account our normal habitual life on Earth. And the changes in posture and bed rest, they do provide or do cause a decrease in blood flow to the brain. But yeah, it's hard to say, but I don't think it's very unlikely that it's due to the direct effect of any changes in perfusion pressure per se. And it seems to be more likely some secondary effects and linked to perhaps fluid shifts or loss in plasma volume, at least as the likely mechanisms. Oops. So all of this work was actually done before I even came to Innsbruck, or in Dr. Levine's lab at the Institute for Exercise and Environmental Medicine. And you can imagine it takes a small army to perform all of these experiments. So I would like to thank everyone that I worked with back then, and I miss them all very much. Now I'm in this part of the world, and of course, I'll be happy to take any questions.
Well, thanks so much, Justin. That was an excellent presentation, as usual. Some really interesting and novel data that you're presenting with some really, as I say, novel designs, experimental designs, and measurements, of course, with your direct invasive ICP measures. So I'm just going to, there's one question in the chat in terms of a reference, I guess, for the CO2 responses to with the supine versus upright response. Just in terms of whether that's a mechanism for why there's no change, or so change cerebral blood flow with no change in pressure.
I can't actually read the comment. I don't know what I've done for now. But so if I understand the question correctly, is the decrease in CO2 causing the decrease in brain blood flow? And I think certainly one would say yes. And there has been some clamping studies to adjust for that, to bring up CO2. But normally it doesn't account for 100%. And neither does, I think, Ben and Rong Zhang have done some sympathetic modulations and looked at sympathetic activity, and also doesn't seem to be completely account for that response. One of the interesting things is that, at least for me, was the part at the end where sometimes physiology moves in the same way. Doesn't mean it's it's correlated, not causative. And it's interesting to me, at least, that the vertebral artery didn't change very much at all with normal changes in posture, but was quite responsive to bed rest. So again, could be different mechanisms, I'm sure, due to, because in bed rest, of course, you have deconditioning on top of anything else. So yeah, I'm almost would have no doubt that CO2 is having a role in the normal gravitational gradients.
Mm-hmm. Absolutely. Thank you. Michel Lesserenza has raised his hand. If you'd like to ask a question.
Hi. Yes. Thank you. Thank you for the presentation. It was very interesting. I was interested in the methodology that you used for the measurement of the hemodynamics in the brain. So I've heard invasive techniques and transcranial Doppler, if I'm not wrong, because I'm working with the time domain and IRS systems, so NIRS. The time domain version, and I see many of application in this field. We are also making some research here in Italy. I'm from Politecnico di Milano, and I was wondering if you've ever used other kind of optical techniques to assess cerebrovascular variations.
So I will say I have many, and I have not been impressed with many. Okay. I'm willing to be impressed, and I will say there was a presentation, and I'm really sorry I don't remember the presenter from Canada just 2 sessions ago, I think, on intracranial pressure, and I came to the session really thinking, okay, this is going to be another non-invasive technique based on NIRS, and actually I left thinking this is a real potential, because most studies don't do what is necessary, and that is a very small graded increase in pressure. Any technique, ONSD, some TCD technique, anything can detect the difference between being head down and head up, something like that, because pressure is 0 and 15. But what we need to know is a technique that can measure the difference between 3 and 8 or 3 and 6. And the presenter from a few weeks ago, she did that. She did really nice controlled experiments, increasing pressure in an animal model, and showed that the teeth, their technique, their nares-based technique, tracked that really nicely. Now, of course, I'm sure there's some nuances to that too, but that's the first time I've ever seen any non-invasive technique where I've been modestly impressed. We in Dallas,
Yes.
because we're doing these invasive recordings, we had requests from everyone, and we never had anything we thought would. I think one had a coefficient of variation of 800% or something, if I remember correctly. So that's my 2 cents worth on non-invasive. And I will say, I think someone said Ben was on the line somewhere, but he won't remember. But my first study I ever did was on ONSD, and he told me that, he told me I wasn't correct, shall we say. And I didn't, and you don't know what you don't even know. So I thought, of course, it was okay. And then when you really take direct measurements of either cardiac pressures, arterial pressures, CSF pressures, whatever it might be, you really understand how careful the measurements need to be, and often how off the non-invasive measurements are. So if you're working in this area, I think it's amazing, and I really hope, if I can help anyway, let me know. But the key is to do these carefully controlled changes in pressure and see if you can replicate that and give the data to someone else. That's really important. Don't analyze it yourself, because there's always a tendency, shall we say, to
bias.
Just to delete the measurement you weren't sure didn't look right, I think, is what I've seen quite often. So yeah, that's my 2 pence worth anyway on non-invasive.
Yeah, that's great to hear. Thank you for your feedback. We many times we hear these kind of feedbacks on optical non-invasive monitoring because of the old continuous wave NIRS devices. And so nowadays we improve the technique, hopefully. And this is why we are having new collaboration also from UT Southwestern and the neurology department, and it's great. It's great to see this kind of application. And when I think about our technology that is going to develop, I see application in your field, and I'm very pleased for that. So thank you for your presentation also.
Yeah, no problem. And like I say, if I can help, if you anything I can do, just send me a note. I'm only across the border.
Okay. Thank you.
Great. Thanks, Michelle. Thanks, Justin. Justin, we have another question in the chat from Pat Prasad. Very interesting talk. Thank you. Do you know if sex and age influences the findings you presented, those from the parabolic flight and bed rest studies?
No, I don't. Unfortunately, we had males and females in the cohort, but often just, it was non-selective. It wasn't on purpose to look at sex differences. I don't know about sex differences. I haven't thought about that too much in terms of pressure in the brain and so on, but I would say aging is really interesting. And at least it's hard to measure these things, but again, I think I mentioned it slightly at the beginning, that you have compliances in 3 circulations, so venous, arterial, and CSF, both at the lower and the upper end. And of course, these are easily changeable with aging, both vascular stiffness and perhaps cerebrospinal fluids, the sac being stiffer, the veins being stiffer. So I can imagine that when you change posture, those all have to align or do change in some way in order to regulate blood pressure correctly and match changes in intracranial pressure with arterial pressure at brain level. So I could imagine that at least with aging, there are quite interesting and different findings, or at least there's a very good hypothesis to think that would be true. But we have never done any measurements yet with aging. And if you want, I could look at the females just to give you a pilot data, but it's definitely not powered in any way to do a statistical analysis.
Okay. Just as a follow-up to that, in terms of the age of the subjects you have on the parabolic flight studies versus the average age of an astronaut, is that kind of comparable?
That's a very good question. Well, the astronauts seem to be getting younger and younger these days. They are not the old cohort that you used to consider. So we had a range. I want to say that most people were 30s to maybe someone in the upper 40s or 50, maybe. But it was sporadic. I think the oldest was 1, and then the most of them were in their 30s, 40s. So not out of the range of modern day, I think, astronauts. That's quite comprehensive. And
Yeah.
only one or two, I think, were younger, in their mid-20s. So, and it didn't really have it was quite, uniform. You know, there wasn't anything very special about any one person that you thought, oh, that was a very interesting response. I think maybe one male had the pressure in the brain didn't go down as you would expect as much. It went down a little bit, but yeah, he also had a very low central venous pressure just resting. So much so that Ben didn't believe me when I came down and made me check and reconnect the catheters, recalibrate the transducers, and I had to prove to him that it was correct. So yeah, it was completely true, but just slightly different.
Sure. I think the last time I checked, the average age of astronauts was about 34 right now.
Okay.
So yeah.
Oh yeah, then definitely I would say 70% or so of the subjects are in that range.
Sure. Yeah. And also, I had a question regarding the use of NIRS again. Not quite the same as Michelle's question, but in terms of measuring tissue oxygenation. So you've presented a lot of data on pressures and flows, but is there anything out there in terms of what's happening at the level of the tissue?
We didn't. We did have once a device from Gary Strangman's lab, and we couldn't get it to work really well. He was super busy in other projects and couldn't really help it. It was more because it wasn't it didn't have an analog output to chart. It was a homemade device, and we never really got it to work. So we didn't get any good data in NIRS. Off my head, I don't remember, but I would think, yeah, if anyone, at least in parabolic flight and on I believe Gary Strangman sent his device onto the space station. So
okay.
I don't know where those data are or if they've ever been published, but there may be some. I think TIMO also, I don't think they measured NIRS. I think they had EEG and TCD in their parabolic flight study. So no, you're right. I'm not convinced. No, I don't know any actually off my head of NIRS studies in parabolic flight. Not really often in bed rest as well, I think, actually.
Yeah.
Now you mentioned it, yeah.
Maybe something there for the future.
Yeah, we have it, so we'll have to stick it on. Never thought.
And actually, Binu Thomas just posted a note. Nice work, Justin. He said we could measure oxygen extraction fraction using MRI in the brain with these maneuvers in the future.
Yeah, that's right. I don't remember, but Binu, maybe we can check. But we did take MRIs in all of these studies. So actually, in all the bed rest studies, all the LBMP studies, we did MRI, and we did it with and without LBMP in the MRI. Lawley Peterson lent her very nice LBMP modified. So we do have it. I don't remember. We didn't take the sequence for oxygen extraction, but we did ASL imaging, diffuse intensity imaging, T1 imaging, and so on. So it is somewhere. It's on the list, shall we say?
Absolutely. Well, thanks so much, Justin. Really appreciate your presentation today. I'm going to hand over to you now to carry on with the introductions and questions for your additional speakers.
Okay, this is where it might go all wrong. Okay, great. Just check, Caroline, you can still hear me now?
I can, yeah.
Okay, great. So I'd like to thank you very much for taking over as the chair of the session. And I'd like to just very briefly move on to our first presenter, who is Carmen Possnig from actually working in my lab. Carmen was actually a physician that I met giving a talk in Graz, because she spent a year on Concordia as the medical physician. And I managed over pizza and some quite good conversation, I hope, to convince her to come and do a PhD with me. And now she is examining, basically forwarding or furthering the research we did in Dallas, looking at blood flow to the brain and bed rest and so on. So without further ado, I'd like to pass over the torch to Carmen.
Yeah, okay. So thank you, Justin, for the introduction. And of course, also thank you, Caroline and Patrice, for the opportunity that I can give a talk today here. So my topic will be the interaction of gravity and diurnal variations on cerebral blood flow. And I'm just going to quickly show you again the data Justin just showed us. So this is data from his 3-day bed rest study. And as we've just learned, with bed rest, there's a decrease in total cerebral blood flow. So this is the baseline data, once in a seated and once in a supine position. And afterwards, the bed rest protocol starts. And we can see already after 1 day, there's a decrease in total cerebral blood flow, which then continues on day 2 and on day 3. So, of course, how you interpret these results kind of always depends on what you compare it to. So what we usually do with bed rest studies, we take the results of day 3 in this case, and we compare it to the supine position, which is, of course, very nice to see changes in the supine position. But the question is how useful that is if you actually want to look at changes due to gravity, because if we look, if we compare it to the seated baseline, we can see that there's actually no significant changes going on here, but that the results of the bed rest are, well, somewhere in between the seated and the supine position. And of course, what we are concerned with when we see this decrease in brain blood flow is a potential hypoperfusion of the brain, and, well, following this, potential impairments in cognitive functions. However, if of course we see the data like this and we compare it to the seated position, cognitive impairments are quite unlikely because, well, usually when we are in a seated or upright position, we hopefully are not, we don't have any problems with cognition in daily life. So if we compare our results to the supine position, we have another problem, which is that this does not really give us an accurate 24-hour profile of cerebral blood flow, as humans usually don't spend their days in the awake supine position, but we are much more likely to be in an upright position most of the time. So what we could, of course, do is we combine those two baselines to give us this 24-hour profile. We could say, okay, we take 16 hours for the seated position to account for the time when we are awake, and we take out 8 hours of the supine position to account for, sleeping time. But of course, the problem we have here is that the supine awake position does not represent sleeping cerebral blood flow. And the second problem that we have is, of course, that these baseline values are taken only at one time point during the day, and we are thus neglecting potential diurnal changes in brain blood flow. So let's have a look at those diurnal variations. What I put here is a paper looking at the circadian profile of hemodynamics, and as you can see, this is a mean arterial pressure as an example, and on the x-axis you have the time in hours starting at noon, and the shaded area is basically nighttime. And as we can see, there is in the afternoon there's a rise in mean arterial pressure, and then again a decrease over the night and a sudden surge in the morning. And the second paper I put here is more about the respiratory control, and also the one typical value we usually look at for circadian rhythms. This is core body temperature, and again on the x-axis we have the time of the day, this time starting in the late afternoon, and the shaded bars again are nighttime, and you can see these quite rhythmic changes in core body temperature over the day. And as another potent regulator of brain blood flow, they've been looking at end-tidal CO2s. And in this case, you have the percentile changes on the left. And you can see that end-tidal CO2, there are actually only very, very small changes during the day. So now we have two potent regulators of cerebral blood flow, mean arterial pressure, which changes quite a lot, and end-tidal CO2, which does not change very, very much. And the question is, what does that give us for the brain. So are there diurnal variations also in brain blood flow? And here the literature is quite unclear. So we have we did find 2 papers that say yes, there are variations. They looked at middle cerebral artery velocity in the morning, in the early mornings, and in the afternoons, and they did find significant differences. But then we also found 2 studies that say no. They also looked at middle cerebral artery velocity, and they did not find any changes throughout the day. So this inconsistency in the literature leads us to the aims of this current experiment, which is, for once, investigating diurnal variations in cerebral blood flow, not only in the middle cerebral artery, but also blood flow in the internal carotid artery and in the vertebral artery to get the whole picture. And also, as I showed you before, the awake supine baseline does not represent sleep. And therefore, we also included sleep measurements with the goal of creating an approximate 24-hour profile that can serve as a model for future bed rest baselines, potentially. So our protocol, I'll just quickly talk about that. So we were measuring our 12 participants so far in a seated and in a supine position. Both positions were randomized between each participant. And there was we had a resting period of about 20 minutes in between the positions to allow for fluid shifts to settle down. We measured every participant at 2 time points during the day. So once at 8:30 in the morning and then again at 4:30 in the afternoon. And the measurements we took were 10-minute recordings of blood flow in the internal carotid and in the vertebral artery with duplex ultrasound. And we continuously measured middle cerebral artery velocity, which we did with a transcranial Doppler probe that was attached to a headset that the participants were wearing. We also measured heart rate and continuous mean arterial pressure with a phenometer, and we measured end-tidal CO2 with nasal cannula. So our nasal cannula was actually quite a fancy device, which does not only measure the exhaled air through the nose, but also with this floppy attachment on the bottom accounts for potential mouth breathing. So it catches CO2 from the nose and the mouth. And I will just show you an example of our 10 minutes recording. So we have on the top end-tidal CO2s, then heart rate, the orange line is the mean arterial pressure. Then below that we have MCA velocity measured with that headset. And on the bottom there's blood flow, first in the ICA and then in the vertebral artery. So you can see that's actually, this is 10 minutes in total. And participants after the afternoon measurements spent the night at the laboratory and slept there while we were again continuously monitoring them with middle cerebral artery velocity, again with this headset, heart rate, mean arterial pressure, and also end-tidal CO2. So we then compared the morning and the afternoon measurements to see whether there are any diurnal variations, and we compared the afternoon to the night to see, to investigate variations during sleep. So let's have a quick look at the diurnal variations. So this is the internal carotid artery, which is of course supplying the anterior and middle part of the brain. This is a supine measurement, and first in the morning, then in the afternoon, and you can see there's no changes happening here. Then the middle cerebral artery velocity, which is of course fed by the ICA. We see also no significant differences here, and the same picture for the vertebral artery, which is of course supplying the posterior part of the brain. And again, there is no significant differences between morning and afternoon. So in summary, we can say that we did not find any diurnal variations for brain blood flow in our study. So this is an example of our sleep recordings. This is about 2.5 hours. And again, we have CO2 in on the top, and tidal CO2s right below. And then the first blue line is heart rate, mean arterial pressure, and on the bottom MCA velocity. And as you can see, this is still the beginning of the night, so values are quite high. And as the night progresses, we can see that there is a decrease both in middle cerebral artery velocity, in mean arterial pressure, and a little bit also in heart rate. But end-tidal CO2 is actually quite consistent throughout these 2.5 hours. So if we look at the numbers for that, this is middle cerebral artery velocity, and the first 2 bars, it's the morning and the afternoon measurement, again in the supine position. And then the dark blue bars, this is the sleeping time separated into different hours. So this is hours 0 to 2 and so on. And as we can see, so hours 0 to 2, 0 is really the onset of the measurement. So people were still a little bit awake, then slowly fell asleep. And as they fell asleep, blood flow decreased, was deepest between hour 2 to 6. And then, well, hours 6 to 8, people were slowly waking up again. And this last measurement is actually of the next morning when people were definitely awake again. So we can see there is a continuous and a significant decrease over the whole sleeping period. And if you look for the mechanisms for cerebral blood flow, we measured end-tidal CO2s, but we did not see any significant changes throughout the entire night or also the day before. We also measured mean arterial pressure, and here we can see that actually during sleep there is, at least for the middle of the night, a significant decrease in mean arterial pressure. And then we also we measured middle cerebral artery conductance, and even if we account for changes in blood pressure, there is still a decrease in conductance. So what we assume from that is that the decrease in middle cerebral artery velocity is most likely due to the oxygen demand for cerebral blood flow to be, the oxygen demand for the brain to be a bit lower during the night. So metabolism in the brain being lower, and therefore the blood flow going down for this reason. So if we average the whole sleeping values that we had for each hour for the whole night, we get a decrease. So here you have again the afternoon measurements for seated and supine and sleep, and you get a decrease of about 20% for the whole night compared to the afternoon supine measurement. And of course, it would be very interesting to see what happens to internal carotid blood flow during that time. And we did not measure it, but since the internal carotid artery does feed the MCA, we assumed that changes would be similar. And we calculated a sleeping value for the ICA from the decrease we saw in each individual person in the MCA, and we found a decrease of about 78 milliliters per minute for the ICA. So our take-home messages. So what do we need in order to have an approximate 24-hour brain blood flow baseline for future bed rest studies? Well, we recommend to take a baseline in a seated position. Once during a day would be enough, as we saw no diurnal variations, and we recommend the seated instead of the supine, as the seated position represents more accurately the daily life changes we usually have. And we also recommend taking a sleeping baseline, as the awake supine brain blood flow does not represent brain blood flow during the night, for which we saw an approximately 20% decrease. And also it would, of course, for future research be rather interesting to see whether the decrease we see in brain blood flow during bed rest is even further amplified during sleep. So it would be really interesting to actually do a bed rest study with sleep measurements included. Yes, so thank you for your attention, and I'm happy to take any questions.
Great, thank you very much, Carmen. You have a few questions that I'll try and read as best I can. So the first one says, thank you very much for the excellent presentation. I was wondering whether the measurements were bilateral. Did you measure the measurements on both sides of the, I guess, either the Doppler or the TCD, or was it just on the left side only?
No, it was just on the left side for every participant.
Okay. And the second one is also about, basically very interesting data, and have you done, I will ask it in a different way because I also know the answer, but Andrew asks, did you assess changes in dynamic cerebral autoregulation during sleep? And it would be interesting to pair this with some EEG data. Yeah,
we did not measure EEG, sadly, and we plan to assess autoregulation, but we haven't. It's still a work in progress, so we haven't done. We're still missing 3 participants, and we will do the definitive analysis after we have collected everybody's data.
Great. And another one from Ronald, and this is actually a really nice, interesting question, a different type of model you can apply. So he says, very interesting data during sleep. It may be interesting to apply. It's what's called a critical closing pressure model. And it's another estimation. So rather than just using cerebrovascular conductance, you could also look at measuring critical closing pressure to see whether this is one of the culprits for the decrease in cerebral blood flow during sleep.
Oh, okay. Cool.
So I guess it's more of a statement than a question because you haven't done it, but yeah, I do also know that the critical closing pressure model, and then he's right. This would be also another thing to measure. Okay,
we can look into that.
Yeah, another. It's a great presentation. Are you able to touch on some of the mechanisms behind why the decrease in cerebral blood flow during sleep was observed?
We measured only end-tidal CO2s, which did not change, and mean arterial pressure, where we did see a decrease. So I'm guessing it's most likely because of those.
Yeah, I think mostly it's about during during sleep. So what are the mechanisms during sleep? Because
that's most likely because the metabolism decreases during sleep. So the oxygen demand being lower because we don't have that many posture changes. We don't have any cognitively demanding tasks to perform. So most likely because of that, I suppose.
I have a great question from Patrice, and I promise you I did not ask him to ask this question, but he said, nice study, and when he's sleeping, he said, I'm moving about a lot. What about your participants? Did you control for potential movement during sleeping, especially from their back to their side?
Yeah, that is a lovely question. Because actually we did not only measure people in a seated and a supine position, but we also measured them during the day in a prone and a lateral position to see whether there would be any changes compared to the supine one. And we did not see any significant changes between those 3 postures. So we suppose that also during sleep, there would not be any change.
Sam asks about some of the regional changes. So again, it's more of a hypothesis, but do you think there's any reason to believe that perhaps there may be differences in the posterior and anterior circulations during sleep? So of course we only measured the anterior part with the MCA, but
yeah, it would be really interesting to also have the PCA measured and compare those two, but with our headset it's only possible to attach one probe at one side, so we could not measure two arteries at the same time, sadly. But yeah, it would be quite nice to see that.
At least while sleeping, anyway, it's hard to see that one.
Yeah.
And one final, again, I think more of a statement, but another good comment from Ronald for us that we couldn't do, but it would have been really important to have correlated the cerebral blood flow stages, the cerebral blood flow changes to the stages of sleep.
Yeah, we did. Sadly, we couldn't see. Well, we couldn't assess the sleep stages, but I do see that with the nighttime recordings, there are changes in cerebral blood flow for shorter periods of time that probably correlate with sleep stages. But since we didn't record those, I can't really tell.
Yeah, this is a shame.
Mm.
Can't measure everything, I guess.
Yeah. It's already hard enough to sleep just with the headset and the phenometer.
Right, good, great. And then I think that's everyone, except for I will ask one question just about some of the other studies, just because it's quite interesting that, at least now that's, if you include our study in the list, there's 3 that haven't really seen any major diurnal variations, but there were 2 that did. And I wonder just, is there any idea why, not a technical error, because I doubt that's the case, at least for some, what's any reason why it could be that some see a diurnal variation and then we don't seem to see that?
Yeah, actually, I do. So those 2 studies I showed earlier, which did show a diurnal variation, I have 2 figures from them here, and one of them I'm a bit dubious as to whether this really is the NCA, as well. They start with a velocity of about 38, and the peak is I guess around maybe 47. So it's possible that they did measure another, like maybe the PCA, and that there is some variation in that one. But yeah, I'm a bit, I'm not convinced that this is the right artery. And for the second study, they did measure, they did see cerebral blood flow to be lower in the morning than in the afternoon. But the thing is, they measured, they took the morning measurements at 6 a.m. and the afternoon at, I think around 4. And 6 a.m. is really very early, and I think it's possible that what they were measuring is maybe not a diurnal change, but rather sleep inertia. So sleepiness basically, so people still being a bit in the night variation of cerebral blood flow, and not it actually being a diurnal variation. Yeah.
I guess in the morning also there's some quite good data where there's a blood pressure surge really at the beginning of the morning, I guess.
Yeah.
People at risk for stroke, so that early morning, if I remember rightly.
Yeah, the stroke risk is higher at the time too.
All right, great. Thank you very much.
Yep, thank you.
We can switch. So the next presenter will be Alex Friend from the University of Bangor. He is actually mentored by a long line of excellent mentors, because Sam Oliver is his mentor and was also my PhD supervisor. So I'm expecting great things today, Alex, from your presentation. And he also does, we thought it'd be nice to mix it up a little bit. In the middle, Alex is going to talk a bit different. So not only about gravitational changes, but also about the laying on top of that some heat stress. So a little bit of a different talk in the middle for us than just pure gravity, I think, Alex.
Fantastic. Awesome. Thank you. So I'd like to say thanks to Justin for inviting me today. And I'm going to share some data that was in collaboration with Professor Igor Mekovic and Justin Lawley, and titled The Resting and Head-Up Tilt Cerebrovascular Responses to a 3-Day Simulated Heat Wave. So just a quick, I guess, whiz-bang tour of the physiology of an acute passive heat stress. And with elevations in skin and core temperature, we get this physiological response for the purpose of expelling heat and trying to maintain a stable core temperature. So what we see is we get this redistribution of blood volume, where we get cutaneous vasodilation, so an increase in skin blood flow of about 5 to 7 liters, for expelling heat through the sweating response, conductive, convection, all of those different mechanisms. And we see a reciprocal vasoconstriction of the non-cutaneous circulation, for example, the splanchnic and renal circulations. So what we have is this competition between maintaining blood volume centrally and the demand of increased peripheral flow to expel heat. So we get an increased cardiac output, which actually then minimizes a reduction in mean arterial pressure. And finally, when core temperature increases by about 1 degree, 1.5 degrees, so just over 38 degrees, we see this hyperventilation response that's induced by hypothermia. So most models looking at this acute passive heat stress use or may use a water perfused suit where they cause this rapid elevation in core temperature. They feed warm water through the suit and it increases your core temperature really quite rapidly. And what we see when we measure cerebral blood flow, particularly they use the middle cerebral artery through TCD, we get this fall in cerebral blood flow velocity. So here we've got an incremental increase in core temperature to the temperature limit, and we can see that the fall in cerebral blood flow velocity starts at about 5% all the way down to 20%. Now, when you overlay a blood pressure challenge to heat stress, we get a compromise to our blood pressure regulation. And here we can see to a response to LBMP protocol that we get an exacerbated fall in cerebral blood flow velocity. So as the pressure incrementally increases in LBMP, our delta cerebral blood flow velocity in the heat stress group in black, you get this greater reduction in cerebral blood flow velocity, which then means that individuals have a lower orthostatic tolerance. So here we've got the proportion of subjects remaining and a cumulative stress index, which is a arbitrary measure of their orthostatic tolerance, so how well they can deal with a blood pressure challenge. And you can see in the red line, we have considerably less individuals who can withstand a orthostatic stress or a stress index compared to the control. Now, generally, these studies, so these acute passive heat stress, are significant magnitudes of change in their core temperature. You can see we're going up to 2 degrees, 1 degree, even up to 4 degrees change in core temperature. And we've got large changes in blood pressure too, either all the way to syncope or incrementally increasing until limit in lower body negative pressure. And so we see that we have these large changes. What's less known or less clear are to do with the modest stress. So looking at less than, I guess, a degree increase in core. That's what's possibly more applicable, where you're not, stuck in a water perfused suit and rapidly warmed very quickly. And the reason I say this is because with climate change going on, the incidence of heat waves are much more often. And particularly, this is a map picture of the European heat wave back in 2003, where in particular in Paris, we had these 10 degrees increase anomaly, particularly in the south of France, where temperatures were reaching above 35 degrees centigrade. Now, this led to considerable deaths and excess deaths. So here from that 2003, for just 2-3 weeks of heat wave, there was a 60% increase in excess deaths. And specifically, these can be cardiovascular deaths where each degree increase in air temperature increases the risk of cardiovascular mortality. And the reason that heat waves are slightly different to these rapid protocols that you see in the lab is it's more of a cumulative heat stress, where not only are you got an increased air temperature, you've also got the prolonged impacts of possible changes in fluid volume, dehydration, even sleep disruption. There's a whole holistic view to this heat stress, which causes it to be a different physiological stress compared to these ones that are conducted in the lab. So you still will have this competition for peripheral and central blood volume, to maintain your blood pressure. But with heat waves, you've got a prolonged, slower onset of this elevated air temperature, which may mean that actually your core temperatures don't rise up as much. It allows time for adaptation. You've got the ability to have evaporative heat stress, whilst the suits don't allow this. And these suits kind of provide more of an incompensatable sledgehammer approach to heating, as opposed to what may occur during a heat wave. So it's not just mortality either. There are some research out there that suggests that there's increased incidence of syncope, and it's not the seasonal changes, maximal daily temperature when you go into the summer months that are causing a greater incidence of syncope or to the emergency department. It's actually 7-day fluctuations in temperature. So it's these short-term rapid fluctuations in temperature, such as heat waves, which seem to cause increase in the incidence of syncope. And you may think as well that, oh, well, all those excess deaths, it might be in the elderly population. Well, it's not just the elderly, it's not the high-risk populations. You've got people who are working in high-intensive or labor-intensive physiological straining work, and everybody is at some risk to syncope and heat waves. So we can investigate the effect of this, I guess I'll call it a cumulative, though I can't pronounce it very well, but a cumulative heat stress on the cardiovascular and cerebrovascular response to rest, and then to a orthostatic stress. And here we're going to use a head-up tilt, which induces a gravitational pooling of blood into the lower limbs. And then to kind of preface it all, the logistics of running a study to mimic a heat wave are just bonkers, are just crazy difficult. So the reason that there's a bit of a gap in this research is because logistics have limited this so far. So I applaud Igor Mekovich's lab to be able to run such a protocol. So our aim and hypothesis is clearly that we wanted to examine the resting and 10-minute head-up tilt cardiovascular and cerebrovascular responses to a 3-day simulated heat wave. And we hypothesized that in comparison to non-heat stress conditions or a control condition, that a 3-day simulated heat wave will reduce resting cerebral blood flow velocity, and we will still see these exacerbated falls in cerebral blood flow velocity to our head-up tilt, our orthostatic challenge. So we had 7 young male participants, and this is for one of the papers that Igor Mekovich's lab has released, and it was nicely explains how they have done the protocol, because it took great length, like I say, to control this perfectly. They used, I think, an Olympic sports facility, which they were able to control the temperatures throughout. And you can see that they've got a 1-day familiarization, a 3-day wash-in, a 3-day heat wave, and a 3-day washout. For interest of this presentation, I'm just interested in the wash-in and the heat wave. And during each day, the temperature was separated into work and rest, so almost day and night, where during the work periods and day periods, like in a heat wave, you'd have hot times during the day, and then in the evenings, it would be cooler. And they were looking to mimic the temperatures in Paris in 2003 in that European heat wave, where between day and night, there was about a 9-degree fluctuation. So during heat wave, we're at 35 degrees, about 10 degrees higher than the wash-in period. And then in the evenings, they were slightly cooler. They controlled the humidity to be at 45 degrees, and then it just fluctuated with what was going on in the day. During the work period or the daytime, they had periods of sitting, stepping task, or this simulated assembly line task in both in the morning and afternoon. And our head-up tilt was completed in some time during the afternoon period between 1 and 6 o'clock. And we had a fixed 10-minute protocol of a 60 degrees head-up tilt. And we took 2-minute samples, incremental samples of, well, we had the core temperature by ingestible pills. We had phenopress-derived cardiac output, heart rate, stroke volume, and mean arterial pressure with middle cerebral artery velocity measured by TCD. We took duplex ultrasound of the femoral blood flow, and we had breath-by-breath and tidal CO2. It's worth noting as well that they didn't restrict diet, they didn't restrict water intake, but they did restrict physical activity. They tried to limit just to the activities that were strictly time frame protocols that they designed. So their core temperatures during the 3-day simulated heat waves. So I broke it down to day and night, and this is the delta, so the change in core temperature compared to the 3-day baseline period, the washing period before. And we've got day 1, 2, and 3 in heat wave. And we see that actually their core temperature increased only by modestly a 0.25 degrees C, but it's still significant. This is the mean average on day 1, and every day and night thereafter was slightly less. And then what I've also added in is the diamonds are actually the mean peak core temperature increase that didn't actually go beyond 0.6 of a degree. So first we'll go and go through the resting responses, cardiovascular and cerebral vascular responses. And for just to explain the axes, we've got baseline on day 3, because by this time they are very familiarized with the protocols, and then heat wave day 1, day 2, day 3. So first we've got the femoral artery, this is vascular conductance, and you can see that at baseline they're at about 1.7 units. And with heat wave, or being exposed to the heat wave, we see this large increase in vascular conductance, which is indicative of peripheral or a vasodilation of the femoral artery, which will be a mixture of muscle blood flow and skin blood flow as it's trying to expel heat from the muscle and out towards the periphery. So this profound peripheral vasodilation is something that we would expect to a heat protocol. Looking at our cardiovascular indices, we see that at baseline, or compared to baseline, we do see what look like small palpitations in the cardiac work, but these were not significant. And as you can see with our cardiac output, it's pretty steady despite increasing a little bit, but it may be just the fact that we only have 7 participants. But more essentially, our mean arterial pressure was actually steady across all days at high altitude at heat wave, during heat wave, compared to baseline. So despite what may look like a little bit of extra work in the cardiovascular response, our blood pressures are maintained. Our end tidal CO2, so we see that actually on day 1 heat wave, we see this heat-induced stress response where we see a hyperventilation response, which then is compensated over time. By day 3, you can see that we have started to adapt to the conditions and we're back to baseline levels. And then when we look at our middle cerebral artery values, there was a reduction and it was sustained across all days during the heat wave, but these were not significantly different. This was a drop of about 7.5 to 8%, but like I said, not significant. Moving on to the head up tilt responses, we start with the heart rate and stroke volume response, where we're seeing that these are delta responses. So with a head up tilt, we'd expect about a 20 beats per minute increase in heart rate. And we're seeing similar across the board during the days at heat wave. And this is compensating for the reduction in stroke volume, which means that our cardiac output is steady, and our mean arterial pressure as well, we see similar plus 10, 12 millimeters of mercury across all days at heat wave. A little bit on increase on day 3, but these were not significantly different. So we've not particularly got any autonomic failure due to the heat wave exposure, and we've got a similar increase in mean arterial pressure to our head up tilt. When we look at our femoral vascular conductance, if you remember, I said that at baseline, our vascular conductance value was about 1.7. So just having a head up tilt with no heat wave, we get this reduction in conductance. So we're seeing a vasoconstrictive response. And this drives a plus 12 millimeters of mercury in mean arterial pressure. And then now when you look at the heat wave protocol, we do see there's a significant fall in vascular conductance. So what we're seeing is that heat stress has an effect to be able to further vasoconstrict the femoral artery to reduce the flow, and we are still maintaining our blood pressure values similar to that was at baseline. our end tidal CO2, so as you would expect with a head-up tilt, we get our hyperventilation response, which was similar across all days heat wave. And this may have contributed to our fall in middle cerebral artery velocity, which is what we would see with head-up tilt anyway at baseline. But what is interesting is we don't actually see these exacerbated falls in middle cerebral artery velocity that we would expect or have seen with rapid elevations in core temperature with acute heat stress. In fact, by day 3, we're even seeing some, I guess, less reduction, so a protective mechanism. So we don't actually see, we see a maintained or a similar reduction is probably should how I word it following a head-up tilt. So our take-home message just quickly, because I'm running over a little bit, is that resting in the head-up tilt cerebral vascular and cardiovascular responses are similar across all 3 days of a 30 degrees heat wave. Specifically, cerebral blood flow velocity was protected during rest and a 10-minute head-up tilt, and this was in young individuals is what we highlight, because things to consider is that 2 different types of populations we may be interested in. One would be females, because they tendency to have a lower orthostatic tolerance, and in particular, I guess, elderly. These are unfortunately the high-risk population that are at risk and are the statistics for this increase in excess mortality. So it'd be really quite interesting to prioritize research in an elderly population to such a heatwave protocol. And then finally, our head-up tilt protocol was a fixed 10-minute protocol, not to syncope, though anecdotally, we saw that during the heatwave protocol, individuals were cycling towards syncope much more, and then their blood pressure would kick back in. It was almost like they were going to, collapse or hit syncope at any moment, but we were limited by our time restraints. So I'd just like to thank everyone who is involved, and I am open for any questions. Thank you.
Great, thank you very much. So first question is from Patrice. It's a very cool study. Did you measure dynamic cerebral autoregulation in these participants?
Just trying to get the questions up. Did we measure dynamic cerebral autoregulation? We did not, but we have a phenomenon. So during the period before in baseline and head-up tilt, if you're talking transfer function analyses and looking at phase and gain, we measured phenopress blood pressure throughout. So we'd be able to have a look at the fluctuations during the whole 10-minute period and the baseline before. So not measured it yet, but I've got the data to be able to do it.
Okay. Great. So let me quickly move through. Ronald also asks, Ronald's getting all the good questions today. So, because I also think it's a limitation, but so are there did we take any other complementary estimates of cardiac output except for using the model flow?
No, not to my knowledge. The only one, was from the model flow from the phenopress. We did take, I can't think how to word it, cuff and thingy for the arm blood pressure, but not for the cardiac output. No.
Yeah, I'd have to remember. I thought I saw Zach on this list somewhere, but there is some data somewhere, and if Zach hears me, he can maybe chime in. But that the phenometer is not so accurate under heat stress. I'm guessing that's because they typically heat them up, like you say, very, very hot, and you're so peripherally vasodilated. The model flow, the volume clamp method, may be a little bit less accurate, but we could check whether under our conditions they're very mildly heat stressed, whether the model flow works. He is there. Zach.
Hey guys, you're right. I think under conditions where it's pretty mild, the model flow it's not perfect, but it's been used. Yeah. So I wouldn't say like the model that the paper that was cited here from Craig's lab, that's like the sledgehammer, right? Really hot skin temperature, rapidly rising core temperature, whereas your model isn't. So I think as long as you understand the limitations, I think it's a fair approach.
Thank you for making me aware.
Thanks, Zach. I also, Anna also mentioned we could have used the Ina core, and yeah, Anna, we could have done, and we do have one, but unfortunately the Ina core had a small, shall we say, technical issue with our Ina core device, in that the tubing snapped about a month before we left for this study. So unfortunately, yeah.
Yeah, no, I'm very interested. I'm starting to jump in those questions. I am having a new lab here at Texas A&M, and we are trying to compare a bunch of different methods. And actually, our inocore also snaps. So I'm glad to hear others have the same issue. But I guess I'll follow up with you offline in a couple of questions about methods and everything. Thank you.
Absolutely.
Great. Great. In that case, if there's no one else, because we're actually doing very well for time, we're almost perfect to finish in 20 more minutes or so, we will switch to the next talk. Okay, the next talk is from Alicia, and she is actually from, did her medical thesis at the DLR. If I remember rightly, looking at quite a nice series of study looking at tilting, but with neuroimaging. So hopefully quite complementary to some of the work that we did also. So we're going to switch back now to the effect of bed rest and gravity on brain blood flow for the final talk. Alicia, the floor is all yours if you can share your screen.
Yeah, so thank you from my side as well for the opportunity to give a talk here today. And I will discuss some of the effects of -12° head down tilt on the intra and extracranial vascular system. And just to give you a quick summary again of the basic principles we have when we look at the cranial perfusion and also at the simulation of microgravity, is first of all, we have a total volume of around 1,300 to 1,600 milliliters of the cranial cavity. And we have basically 3 compartments within there. The first one being the brain tissue, and then the blood and cerebrospinal fluid CSF compartment. And now basically when it comes to intracranial pressure, the most basic principle is the Monroe-Kelly doctrine, just stating that any volume change in one of the compartments must be compensated by the other ones, or otherwise we will have an increase in intracranial pressure. And as stated in the talks before, there is a possibility of compensation due to the connection to extracranial spaces. And then the second basic principle is, again, just to show the fluid shifts and how they connect between head down tilt and zero gravity. So first of all, when you tilt the subject to head down position, you have a change in the direction of the hydrostatic pressure from the feet towards the head, which will ultimately result in a net flow of fluids towards the head. And similarly, you have a change in the net flow when you compare zero gravity to the standing position under gravitational conditions, simply because the hydrostatic pressure ceases to exist. And as we've seen before as well, is if you have a closer look, it's getting much, much more complicated, because not only you have the shifts of the fluids towards the head, but also you have cranial shifting of the abdominal organs, and both of which eventually affect respiration. And since respiration is closely linked to the venous bulk flow, we have an effect on the intracranial venous system. And due to the link between venous and CSF flow, again, we have an effect, although it's an indirect one, of the respiration to the CSF flow. And via the lymphatic system, we also have a connection to sleep. And obviously, via the arterial system and the effect of the fluid shifts there and the cerebral autoregulation, we have a connection to the systemic cardiovascular system as well. Now, out of all these interconnections, we formed the following hypothesis. The first one being that due to the decrease in the cranial perfusion, which was up to 15% in -12° head down tilt, and the increase in the venous congestion would result in a decrease in cognitive performance. And the second one was that due to the cephalic fluid shifts, we would observe an obstruction of the upper respiratory tract and thus an impeded sleep behavior. And to test for these main hypotheses, but also with an emphasis on the cerebral perfusion, we performed the IPCOG study in the NVHAP location, which you can see here on the right. at the German Aerospace Center in Cologne. And the study itself was conducted as a crossover study in which we compared the -12 degrees head down tilt to supine position. And for that, we recruited 13 male subjects. You can see mean age, height, and weight down below here. And what's important to mention at this point is that each of the subjects actually participated in 2 campaigns. And one time they spent the interventional phase in supine position, and the other one they were tilted. For the statistics, we used the R program, more precisely the linear mixed models. And for the study in general, we used the per protocol approach. Now, if you have a closer look at the methods, obviously we had a cognitive test battery because that was the main outcome of the study. But as we wanted to assess the connection between the cognition and the perfusion, we had also quite a lot of perfusion measurements. The first one was a transcranial Doppler flow measurement of the mid-cerebral artery. We also had ultrasound measurements to assess the frontal tissue thickness and the cross-sectional diameters in the venous system. And then we had a near-infrared spectroscopy for the front, in which we assessed the tissue saturation index. And finally, for the daily measurements, we also had MRI pictures, and for the night, we had polysomnographic recordings. Now, to be more closer on the MRI and the ultrasound, for the MRI, we used a 3 Tesla scanner with a 16-channel head neck coil. And among others, we also performed phase contrast imaging, and we used the magnitude pictures of that to assess the bulk flow of the main cerebral vessels of the intra and extracranial system. And for the BMR ultrasound, we used a MyLab 25 scanner to assess the frontal tissue and the venous system. Now, coming to the campaigns themselves, as I already said, each of the subjects participated in 2 campaigns, once with the interventional phase in horizontal position and once in -12 degrees head down tilt. Now, the campaign itself actually started on day 1, which was merely there for the adaptation. So the subjects would arrive and they would get acquainted to the new surrounding and the other persons they were performing the study with. And we also gave them the first introduction to the cognitive test battery. And then during the first night, we applied the polysomnographic devices without actually analyzing the data. And that was due to hopefully decrease any effects of the first night effect on the polysomnographic data. And then we actually started the main measurements with the baseline data collection on the morning of the 2nd day. And the interventional phase itself started during the 2nd measurement block on day 2, lasted over the 2nd campaign night until the end of measurement block 3, which was about 21 hours later. Now, I've already explained the methods we used, and all of these methods were always performed in the same order throughout all the measurement blocks. So we started with the spectroscopy and the Doppler, then proceeded to the cognitive test battery, and then the MRI measurements, and finally the ultrasound assessment. Now, we performed a total of 10 campaigns, and as I already said, we had initially 13 subjects, but unfortunately we had 2 dropouts, and the first one was subject H, who dropped out due to gastroesophageal reflux and consecutive vomiting at the -12 degrees head down tilt. And then we had subject O, who dropped out due to family issues in the first of his campaigns, campaign 7. So the results I'm now going to present are those of the remaining 11 ones. And I will also concentrate my presentation on the results from the ultrasound and the phase contrast imaging. However, I'm happy to give you further information on the cognitive test battery and sleep data as well, if you're interested later on. Now we start right up with the ultrasound measurements. And what you can see here is the minimum and maximum cross-sectional areas of the internal and external jugular vein. And we found a significant increase in both the minimum and maximum area of the internal jugular vein on both interventional days and -12 degrees head down tilt, while with the external jugular vein, only the minimum cross-sectional area was significantly affected and increased during the head down tilt. Now with the frontal tissue thickness, we although we saw a tendency of an increase at the head down tilt position, it wasn't quite significant. And it was stronger actually in the first day. And now we come to the quite interesting results from the phase contrast imaging, because they weren't quite what we were expecting actually. So first of all, when we look at the external carotid artery, and what you can see here is the mean flow of all these vessels. And what we can see is that we actually had a significant increase in the inflow via the external carotid artery during the head down tilt position, while we could not reproduce the significant effect on the flow on the internal carotid artery. Yet what we saw, and this was really astonishing, is that we actually saw an increase in the outflow of the internal jugular vein on both days at the head down tilt position. The other vessels, so the external jugular vein and also the vertebral arteries, they weren't significantly affected by the body position. And just to show it to you in a more graphic way, what you can see here is actually the data from day 1, and the numbers here indicate the difference to the baseline data we assessed in supine position. And as you can see, there's nearly no difference between the horizontal and head down tilt position when you look at the external carotid artery in the external system. However, this striking increase in the inflow I just shown you in the table before in the external carotid artery. And similarly, when you look at the internal jugular vein, we have this striking effect on the outflow. So just to summarize that and give potential reasons or follow-ups. First of all, when we look at the cross-sectional areas, that was actually quite as we expected. So we saw an increase, and that's been reproduced by several studies before and also afterwards, and indicates for venous congestion. But now if you look at the external carotid artery and the increase in the mean flow, one thing that might come to mind there is that this might be a potential underlying cause for the fluid congestion, the interstitial ones you see especially in zero gravity, and to a lesser extent also in the head down tilt position. That's an effect normally known as the so-called puffy phase. And secondly, when you now combine the internal jugular vein and the significant increase in the outflow with the increased inflow via the external carotid artery, one possible explanation might be an increase in the, there might be a collateralization between these two systems, and that would actually have quite some interesting implications for the whole cerebral perfusion and also the space-associated neuroocular syndrome Justin just mentioned in his talk as well. Because if we just go to the initial graph again I showed to you, obviously if we have an effect on the venous system due to a collateralization via the external system, then we would also see an effect on the cerebrospinal fluid system. So that's actually, as I said several times, that's not really what we expected at all concerning the internal jugular vein. And I'm quite happy to hear your opinions on that and get your feedback on that. But before we come to that, I would first of all thank the whole team of the Muscle and Bone Metabolism Department at the Institute of Aerospace Medicine who conducted the study. And I would also like to thank the subjects participating, because otherwise we wouldn't have been able to assess any of the data. So I'm looking forward to your questions, and yeah, thank you.
Great, thank you very much.
Always.
As always. Let's see, my questions, are there any yet? No, there doesn't seem to be any questions yet. Maybe they're running out of ideas towards the end of the afternoon, at least in European time. I have one, I guess, or two questions or comments. And I think one of the things you saw was, if I'm right, an increase in blood flow in the external carotid artery, which is of course perfusing the face. And I think that also was recently shown. I think Ogo had a paper in Journal of Applied Physiology. And I wonder how much that's just basically perfusion pressure you know the same thing, that if you're 15 degrees head down, then from the heart to the face, there's an increase in pressure now because of that hydrostatic column. And the face doesn't really have, as far as I'm aware, a very intricate autoregulatory system. So basically it just becomes pressure passive. And almost like the eye, I think the eye also, interestingly enough, some parts of the eye, the choroid or the retina, are different. Some have an autoregulation and some don't. So perhaps at least the increase in flow, maybe if you calculated the hydrostatic difference and then calculated external carotid artery vascular conductance, then you could work it out, because whether it's just purely pressure driven or whether there's really a dilation inside the face itself.
So yeah, we didn't do that during the study because at that time we didn't have that much data actually on the external system.
Yeah.
But obviously that might be one of the main causes which increases the inflow via the external carotid artery, or not the inflow, but which might cause the results.
Mm-hmm. Yeah, I don't really have at least any. See if there are any other questions. I can also, there's not yet, but I don't have any great ideas for your increase in venous outflow, if I'm honest. Yeah, that's quite interesting.
Yeah, I think what you always have to take in account, obviously, with the head down tilt studies, is that you don't have a lot of subject participating, like with all the others. But still, that's actually why we were thinking about the collateralization, because we, as I said, we didn't expect that at all. So, and it might work due to the fact that the external veins, so they actually do have the valves, and so the hydrostatic pressure is potentially working against the opening because of the column pressing against it. So yeah, it might be a potential explanation, but yeah, as I said, we're still working on that because that's not what we expected.
Yeah, I don't know. I mean, one thing perhaps you could check. I mean, again, we did the same in parabolic flight, and we've done it with bed rest as well, is that the veins, of course, they also distend because also the pressure is greater. So you notice it. I think one of the most interesting sort of observations is the difference between what you're doing here and parabolic flight and space flight. In both conditions, you see a bigger jugular vein. But in parabolic flight and space flight, that's because mostly, at least in my opinion, is you lose tissue weight. So when I'm lying down, the weight of my neck or the tissue is compressing the artery, the veins. Yeah. And when space, and you notice it, because I have images, is the vein becomes perfectly circular in space flight or in zero G, where what you're doing is probably increasing the pressure. And I wonder if you look at the Doppler waveform, perhaps you can see whether this is a suction, whether because if they're breathing a bit heavier because they're in the head down tilt position, perhaps it's more of a respiratory suction of some kind. That's a complete guess. I literally have no idea. Because if inflow is not changing, normally outflow also would be similar, unless it's moving through different counterlateral vessels. So could be maybe some breathing mechanics. So,
yeah, that's a good point with the Doppler measurements, actually, because we obviously we assessed the velocity, but we didn't look that close at the waves. So we could do that again. That's actually,
it's normally pretty obvious, when you're in the vein and someone goes and breathes in, you see the venous flow changing. Okay. Then if there's no other questions, we can call it a wrap, because that's exactly 8 o'clock plus 1 minute. So even I can't do any better than that for timing. Caroline, I hand it back.
Thanks, Justin. I think Carmen had her hand raised as well. I don't know if she'd like to ask a question.
Yeah, sorry, just a quick question. I was just wondering about the outcomes of the cognitive test battery that you were doing, Alessa.
So basically, just to summarize it, we saw an effect, but mainly on the second day. But the subjects also reported they had quite difficulties in sleeping at the down tilt position. So you definitely have to take that into consideration when you interpret the results. But the main effects were actually on the second day that we saw a slight impeding of the cognitive testings.
Okay, thank you.
Okay, well, thanks so much, Justin, for your great presentation and chairing of the remainder of the session, and also to the abstract speakers. They're all excellent talks and a really unique array of topics today. So thanks so much. Just a note here, this is what I'm calling part 2 of the gravity story, I guess, in some ways. So on the 14th of June, our next session is really focused on the effect of changes in intracranial pressure on cerebral blood flow, so really extending on the work of Justin today. And we have 2 featured speakers, actually. We have Syed Imaduddin, who's presenting on a non-invasive estimation of ICP. And then Professor Iwasaki will actually be presenting the work where they applied this technique to astronauts, so assessing the effect of long-duration spaceflight on ICP and cerebral blood flow. And then we have 2 abstracts from trainees where they're examining different techniques to modify intracranial pressure and then assess the effects on ICP, the effects on cerebral blood flow. So I'll be sharing that session on June 14th, and that will be the last session for the series in this semester. So we look forward to seeing you all there, and thanks so much for your attention today. And I'll see you soon.